Dear students, so in previous class we were discussing a theorem. So for let X be a non-vector space, X be a non-vector space, A is a compact linear operator on X, then set of all K with a K following sigma E of A where K differs from 0 equals set of all K such that K following sigma A with the K differs from 0. So the proof of this theorem, in the proof of this theorem we already proved that A minus Ka is bounded below, A minus K is bounded below, comma, it is injective, and A minus K is surjective. Okay. So now come to the rest of the proof. So we also A minus K all power n. A minus K all power n equals some an minus kn I, where an is A power n minus nc1 A power n minus 1k plus nc2 A power n minus 2k k square plus etc. minus or ncn minus 1 as A k power n. So it is treated as some A. So it is an minus kn I. Agreed? Okay. We have, so an minus kn is A minus ka all power n. Also A minus k is injective. A minus k is injective. Therefore A minus k all power n is also injective. Hence an minus kni is also injective. Then we also know that also in that proof we have a range of A minus ki. We already proved this result also. Range of A minus ki is closed in X. Okay. If you replace A by an and K by kn, what do you get? So it is a range of an minus kni. Range of an minus kni is also closed subspace of X. Closed in X means it is closed subspace of X. Okay. Closed subspace of X. So what is range of an minus kni? Range of an minus kni is nothing but it is yn. Agreed? Now since yn plus 1, what is yn plus 1? Yn plus 1 is a part of yn. Since yn plus 1 is a part of yn, and yn plus 1 equals, what is yn plus 1? Yn plus 1 equals A minus ki or an is A minus ki into yn. Yn plus, we know that yn plus 1 is a part of yn, and yn plus 1 is A minus ki of y. Then there by previous arguments there exists a non-negative integer m such that ym plus 1 equals y. This is already the result. This is a well-known result. So this is the result proved by or proved in the previous class. Okay. So there exists a non-negative integer m such that ym plus 1 equals y. If m equals 0, what happens? If m equals 0, then y1 equals y0. If m equals 0, y1 equals y0. If m greater than 0, then there is a claim. This claim is ym minus 1 equals ym. Ym equals ym minus 1. This is our claim. Ym plus 1 equals ym. If m equals 0, y1 equals y0. This is already proved. Now claim ym equals ym minus 1. How to prove this one? When m greater than 0, when m equals 0, y1 equals y0. When m greater than 0, then our claim is ym equals ym minus 1. So how to prove? So for let y fall in ym minus 1. What is ym minus 1? That means y equals, what is ym? Yn plus 1 is A minus ki of yn. or yes, a minus ki of yn means ym minus 1. In yn plus 1 is a minus ki of yn. So that is a minus ki all power n of y. Agreed. So it is y equals, it is a minus ki all power m minus 1 of x for some x falling x. Agreed. Okay. Why? Because an minus kn is a minus k all power n. So let y fall in ym minus 1. Surely this y equals a minus k all power m minus 1 of x for some x falling x. Then operate a minus k on both sides. So it is a minus k of y equals a minus k of a minus k all power m minus 1 means a minus k all power m of x for x fallen x. Agreed. So that means since ym, what is ym? But ym equals ym plus 1. It is given ym equals ym plus 1. Therefore, there exists ym equals ym, but ym equals ym plus 1 means there exists some set fallen x such that a minus ki of y equals a minus ki all power m plus 1 of z, where z fallen x. Okay. So that means a minus k of y equals a minus k all power m of x, as well as a minus k of y equals a minus k all power m plus 1 of z. So that means a minus k into y minus a minus k all power m of z equals 0. Okay. But a minus k is injective. F is injective, f of x equals 0, that should imply x equals 0. Here a minus k is injective and a minus k of this one equals 0, that means y minus a minus k all power m of z equals 0. That means y equals a minus k all power m of z. So that fallen will, so y equals a minus k all power m fallen z. So a minus k all power m of z fallen ym. So that means y is chosen from where? When y is in ym, so here ym equals, here y is in ym minus 1, here that y fall in ym, that means ym equals ym minus 1, hence our claim is justified. Okay. So when m equals 0, result is finished. When m greater than 0, our claim is ym equals ym minus 1, that is also justified. Now, also since when m greater than 1, we also see that when m greater than 1, we also prove that ym plus 1 equals ym equals ym minus 1 equals etc. equals y1 equals y0. So, okay, but what is y1? But y0 equals x. But we know that y0 equals x. And what is y1? y1 is the range of a minus k. Agreed. So that means y0 equals x, y1 equals range of a minus k, and ym plus 1 equals ym minus 1 equals y1 equals y0. So from here clearly a minus k is, then that means a minus k is surjective. Okay, a minus k is surjective. So that claim is also justified. Agree. So here we have a minus k is surjective. Here a minus k is bounded below. A minus k is bounded below. A minus k is surjective. That means a minus k is, because of a familiar result, a minus k is invertible. Okay, a minus k is invertible. A minus k is invertible. That means every non-zero spectral value of A is an eigenvalue of A. Every non-zero spectral value of A is an eigenvalue of A. That is sigma A is a part of sigma E of A. First we assume that, assume that it has K is not an eigenvalue. Here a minus K is invertible means K is not a spectral value. So its negation implies every non-zero spectral value of A is a non-zero eigenvalue of A. Every non-zero spectral value of A is a non-zero eigenvalue of A is an eigenvalue of A. That means sigma A is a part of sigma E of A. But we already know that sigma E of A is a part of sigma E. This is a non-result. So combines, what do you get? Sigma A equals sigma E of A. So this is the proof. Clear? Okay. So we first assume that K is not an eigenvalue. Finally we prove that A minus K is invertible means K is not a spectral value. So its negation implies every non-zero spectral value is an eigenvalue of A. That is sigma A is a part of sigma E of A. But we know sigma E of A is a part of sigma A. This is a well-known result. So combinedly we have sigma A equals sigma E of A. That is what we recurse. Agreed? Okay. Now, come to the next result. If X is let X be a normed space, X be a normed space, A is a compact linear operator on X. If X is infinite dimensional, if X is infinite dimensional, then 0 fall in sigma A of A. 0 is an approximate eigenvalue of E. If X be a normed space, A is a compact linear operator, and if X is infinite dimensional, then 0 is an approximate eigenvalue of E. How to prove this one? So the proof depends upon the previous lemma or the previous theorem. Here, suppose let X be an infinite dimensional. Let X is infinite dimensional. Infinite dimension. Consider an infinite linearly independent subset. Consider an infinite x1, x2, x3, etc. being an infinite linearly independent subset of X. First we assume that X is infinite dimension. Then consider an infinite linearly independent subset of X, that will be x1, x2, etc. of x1, x2, x3, etc. of X. Now let us Zn. Let Zn equals span x1, x2, etc. x. Zn equals span of x1, x2, etc. xn, where n equals 1, 2, 3, etc. Clearly, this Zn being a proper subspace of Zn plus 1. Clear? Zn being a proper subspace of Zn plus 1. But Zn is finite dimensional. Since Zn is finite dimensional, clearly each Zn is closed in X. Why? Because we have a theorem. If X be a normed space, it's an important theorem. X be a normed space, Y be a proper subspace of X. If Y is finite dimensional, then Y is a proper closed subspace of X. Okay. So since Zn is a subspace of Zn plus 1, clearly Zn is span of this x1, x2, etc. xn, means Zn is finite dimensional. Hence, since Zn is a proper subspace of Zn plus 1, surely Zn being closed in X. Okay. Then by Rees lemma, what is the Rees lemma? There exists some Zn plus 1 fall in Zn plus 1, small Zn plus 1 fall in capital Zn plus 1, such that with a norm Zn plus 1 equals 1, norm Zn plus 1 equals 1, and the dimension of Zn plus 1 greater than or equals 1 by 2. That is by Rees lemma. Okay. By Rees lemma, since Zn is a closed subspace in X, then there exists some Zn plus 1 fall in Zn plus 1 such that norm with the norm Zn plus 1 equals 1 with the distance between, not dimension, distance of Zn plus 1 or Zn plus 1 Zn greater than or equals 1 by 2. Since A is in CLX, A is a compact linear operator, and assume A is bounded. Assume A is bounded. A bounded means there exists some beta positive such that beta norm x less than or equals norm Ax. Beta norm x less than or equals norm Ax for all x of all in x with a beta greater than 0. Okay. Then consider norm Azn minus Azm for n differs from m. Norm Azn minus Azm equals norm A of Zn minus Zm, which but norm Ax less than or equals beta norm x, norm Ax greater than or equals beta norm x, so it is greater than or equals beta into norm Zn minus Zm. Okay, greater than or equals beta into norm Zn minus Zm. But Zm and Zm are falling where? Zn. Zn is a part of Zn plus 1. So distance between Zn and Zn plus 1 greater than or equals 1 by 2 means distance between Zn and Zm for n differs from m. Distance between Zn and Zm greater than or equals 1 by 2. That means norm Zn minus Zm greater than or equals 1 by 2. So it is greater than or equals beta by 2. Okay. Means norm Azn minus Azm greater than or equals beta by 2. That means Azn does not converge. Azn does not converge, or Azn doesn't have a convergent subsequence. Hasn't a convergent subsequence. Azn doesn't have a convergent subsequence. That's a contradiction to the choice of A. Why? Because A is a compact linear operator. When A is a compact linear operator, we already proved that theorem. When A is a compact linear operator, then for every bounded sequence in X, then Axn has a convergent subsequence. Here when norm Azn minus Azm greater than or equals beta by 2, then here we can conclude that Azn doesn't have a convergent subsequence. That's a contradiction to the choice of A. This contradiction is due to our wrong assumption. Therefore, A is not bounded below. Assume A is bounded. So, that's a contradiction. This contradiction is due to our wrong assumption. Means A is not bounded below. A is not bounded below means 0 is present in sigma E of A. Okay. A is not bounded below. That means 0 is present in sigma A of A. 0 is the only approximate eigenvalue. Agree? Okay. So, come to the next theorem. Here the theorem states that sigma A, when X is a non-linear space, A is in CLX, means A is a compact linear operator, then sigma A of A equals sigma A. Sigma A of A equals sigma A. When X be a non-linear space, A is a compact linear operator on X, then show that sigma A of A equals sigma A. How to prove this one? If X is finite dimensional, what happens? Proof. Come to the proof. If X is finite dimensional, then when X is finite dimensional, A fall in CLX, clearly a rank of A. Rank of A is finite dimensional. Rank of A is finite dimensional. When rank of A is finite dimensional, then sigma A of A equals sigma A. Hence sigma A of A equals sigma A. Why? Because let X be a normed space, A is in BLX and finite rank, then we have, that's a well-known result. If X is finite dimensional, A for in BLX, A is a bounded linear operator on X. then is of finite rank. A is of finite rank. A is of finite rank. Then we know that sigma E of A equals sigma A of A equals sigma A. Okay. So when X is finite dimensional, it is only given X is a non-linear space and A is a compact linear operator. We have to show that sigma A of A equals sigma A. So there are two cases arises. First one, X is finite dimensional. Secondly, X is not finite, means it is infinite dimension. When X is finite dimensional, the proof is immediate. Why? Because we have a result. If X is finite dimensional, A following BLX is of finite rank, then we already proved this theorem, sigma A of A equals sigma E of A equals sigma E. So here clearly sigma A of A equals sigma A, so theorem finished. Case second, if X is infinite dimensional, when X is infinite dimensional, when X is infinite dimensional, what happens here? Then when X is infinite dimensional, we already proved that 0 is only an approximate eigenvalue of A. 0 fall in sigma A of A. Okay. Also, we know that also we have sigma E of A is a part of sigma A of A is a part of sigma A. This is again a well-known result. Sigma E of A is a part of sigma A of A is a part of sigma A. Then, but 0 fall in sigma A of A, and we also show that sigma A equals sigma E of A by the first part of by the previous theorem. Sigma A equals sigma E of A. So 0 fall in sigma A of A. Sigma E of A is a part of sigma A of A, part of sigma A, but sigma A equals sigma E of A. Therefore, yes, sigma A of A equals sigma A. Okay, sigma A of A is a part of sigma A. Therefore, sigma A of A equals sigma A. Clear? Yes. So when X is finite dimension, that's immediately follows from the well-known result. If X is infinite dimensional, then we also already proved that 0 is an approximate eigenvalue of A, and also we know that when X is infinite dimensional, sigma E of A equals sigma A. Okay, but we know that sigma E of A is a part of sigma A of A is a part of sigma A. Sigma A equals sigma E of A. Therefore, sigma A of A equals sigma A. Why? Here, sigma E of A is a part of sigma A, and sigma A of A is a part of sigma A. But here, sigma E, since sigma A equals sigma E of A, or sigma E of A equals sigma A,